I am going to demonstrate setting up a thermal mixing simulation in a pipe assembly. So the first thing that I'm going to do is search for the product from the PLM database. So you can see that I have searched using my trigram, which is my identity, and a bunch of different products have shown up. So the first thing that I'm going to do is I'm going to explore the pipe assembly that I found in my database. So as you can see that the pipe assembly product is open now. I still cannot see much, so what I'm going to do is I'm going to expand the product structure, and as I expand I can see different parts that form this pipe assembly. Now I'm going to open the pipe assembly and go ahead with setting up the flow simulation. So as you can see, the pipe assembly has two inlets and one outlet. I'm going to set up a thermal mixing simulation. So the fluid is going to flow in from one side, and the fluid is also going to flow in from the top inlet, and the fluid that enters from the top inlet, that fluid is going to be somewhat hotter than the fluid that is entering from the left inlet. So as the fluid comes in, as the cold fluid and the hot fluid comes in, they mix at the back end, and one of the things that we want to study is that we want to see if there are any hot spots that could have come on the structure. So now what I'm going to do is I'm going to access the fluid scenario creation app from the V+R quadrant, and I'm going to set up a flow simulation. So as I do that, I'm going to select flow as the simulation type, and I'm going to hit OK. So what that does is it creates a flow simulation which we are going to run later in order to get our results. Now, one of the things that you should note quickly is that you are now in fluid scenario creation app. So this is the app, essentially the main app, which allows you to create flow simulations. Now the first thing that I'm going to do is show you how to navigate between modeling scenario and results. So you can see that there is a small glyph right there which you can click in order to select modeling scenario and results, and that's essentially the easiest way to flip between model scenario and results. So right now I am in scenario creation, so I'm going to create a scenario. The first thing that I'm going to do is, what I need to do is create a finite element representation for my model. So a finite element representation is really a container which contains the elements and nodes for the model. So now I created the finite element model, so that I'm all set at this point. Now the next thing that I'm going to do is I'm going to set up the fluid model. So in order to do that, I will have to shift from modeling to from scenario to modeling. So one of the things that you should find handy is that if you press F3, the specification tree shows up, and you can navigate a lot of model structure from the specification tree. So you can alternatively press F3 and you can bring up the specification tree to help you navigate through different attributes. So now what I'm going to do is I'm going to switch to modeling and keep setting up the fluid model. So now you can see that we are in fluid model creation app. Now the first thing that I'm going to do is to specify a fluid domain. So you can see that I do have the CAD for the pipe assembly, but I don't have a CAD representing the fluid volume itself. So that is one of the significant benefits of the flow modeling capability within 3DExperience platform, is that you don't really have to extract the fluid volume. You can just specify the fluid domain and you should be all set. So that's what I'm going to do now. So as you can see that I clicked on the fluid domain icon, and now what I'm going to do is I'm going to specify my fluid domain. So I'm going to keep the flow domain as internal, and then what I'm going to do is for parts I'm going to select all the parts that are available or that form the pipe assembly. The next thing that I'm going to do is I'm going to pick a region, and the idea of region is that it essentially specifies where the fluid domain lies. So in this case what I'm going to do is I'm going to just pick a face, and I'm going to pick a direction, and that direction is going to tell me where my fluid domain lies. So in this case the direction is going to be inwards. So you can see that I am picking a surface, and you can also see a small glyph that has been that comes up, and that glyph essentially shows the direction in which the fluid region will lie. So in this case the fluid region is going to be inside the pipe assembly. So once I have that, what I'm going to do now is create inlets and outlets. So the idea of inlet and outlet is really to cap off the volumes so that I can tell exactly where my fluid domain lies. So in this case I'm going to pick a set of edges that close the fluid volume completely. So now I'm going to create my first inlet. So in this case I'm going to pick the two edges that are that represents the first inlet, and once I pick those edges, my first inlet has been defined. Now what I'm going to do is I'm going to define the second inlet. So again I'm going to pick the edges of the second inlet, and what that does is it defines the second inlet. Now I'm going to define the outlet, which is open to atmosphere. So again I'm going to repeat this process, and I'm going to select the edges to cap off the outlet as well. So once I hit OK, the fluid domain specification is complete. When we perform the meshing, the mesher will automatically extract the fluid domain, and it will mesh it as well. So this process is really straightforward, and it saves a lot of time because you don't have to extract the fluid volume by performing a number of Boolean operations and so on and so forth. So now what I'm going to do is I'm going to specify or pick a material property for my fluid that's going to flow through the pipe assembly. So I'm going to search for a material called water. This material is also stored in the database, in the same database, and as I find it, I can see that there is a material called water, and I'm going to just pick it, and I'm going to apply it to my fluid domain. Note that when you are applying the material, you can apply it to the fluid domain glyph, and what that essentially does is it assigns a uniform material property to the entire fluid domain. Now that the material assignment is complete, I'm going to assign a fluid section to my fluid domain. This step is really straightforward. You pick the fluid section tool, and then you again pick the fluid domain glyph, and you can see that the material that you chose before, that has automatically been populated, so you don't have to really do much there. And then once you are done, you just hit OK, and your fluid section definition is also complete. Now that the fluid domain specification is complete, material assignment is done, section assignment is done, we are going to shift to meshing, and we are going to define the mesh for this particular model. We are going to so one of the things that you should notice now is that the app has automatically changed to mesher. So that's pretty neat. And now what I'm going to do is I'm going to use Hex Dominant meshing for this particular model. So as I bring up the Hex Dominant meshing option, you can see that the fluid domain is automatically selected. And one of the things that you can do in meshing is that you can choose to initialize the mesh settings from support. So what that will do is it will pick appropriate minimum and maximum sizes from the geometry for mesh specification. But in this case, you can see that the minimum size is pretty small. So what I'm going to do is I'm going to set a minimum size of 1 millimeters. Other thing that you can do is you can activate boundary layers. So in this case, what I'm going to do is I'm going to create a boundary layer mesh with first layer thickness of 1 millimeters and 4 boundary layers. The next thing that I'm going to do is I'm going to specify the meshing in parallel, to run the meshing in parallel. So in this case, I'm going to choose 4 as number of threads so that my meshing runs in parallel. You can also choose to specify local specifications, which basically means that you can define regional mesh settings on a volumetric basis or on a basis of local edges. So in this case, I'm not going to use the local specifications. One of the other things that you can also do is you can hit mesh right here and create the mesh as well. But you can also just select OK and save the mesh settings and let the process generate the mesh during the job submission. So now my meshing setup has been done. I am going to shift to model creation. The modeling part, and now I'm going to go back to scenario to set up the rest of my fluid model. So now the first thing that I'm going to do is I'm going to define the physics for my flow model. So I am choosing the flow regime toolbar, and I select temperature for energy equation, and I also select realizable K epsilon as the turbulence model. So we are going to do thermal mixing simulation with turbulent flow. I'm also going to specify initial turbulence. Again, you have to specify these properties on the fluid domain glyph because you really don't have a fluid domain per se right now. That fluid domain will be extracted during the meshing process. So I'm going to specify an initial temperature of 300 Kelvin on my entire fluid domain, and that's about it for the initial temperature. Now I'm going to specify the initial turbulence for my model. you have to select the fluid domain glyph in order to specify the initial turbulence. What I'm going to do is I'm going to keep the default values for turbulence intensity and turbulence viscosity ratio, and I'm going to specify 1 meters per second as the velocity scale for my model. So with that, the initial turbulence specification is also complete. Next thing that I'm going to do is I'm going to specify analysis procedure for my model. So in this case, I'm going to run a steady state simulation, and what I'm going to do is I'm going to specify 200 as the maximum number of iterations. You can also see that there are a number of controls that are available for let's say pressure equation, momentum equations, turbulence equations, as well as energy equations. But in this case, we are just going to stick to the defaults, and we are just going to go ahead. Now we are going to set up boundary conditions for my model. So the first thing that I want to do is I want to create a default wall boundary condition for my entire domain. So this default wall boundary condition will be applied everywhere. This is a no slip, no penetration wall boundary condition. Now any other boundary condition that I apply subsequently, those boundary conditions will have a higher priority, so they will be honored. The default boundary conditions will only be applied to places where you have no other boundary conditions that are applied. Now the first thing I'm going to do is I'm going to apply a velocity inlet boundary condition at the first inlet. So I'm going to pick the first inlet. In this case, again, I'm going to use the glyph for the fluid domain, and I'm going to specify an inlet velocity of 1 meters per second, and I'm going to specify inlet temperature of 300 Kelvin. Also, for the boundary conditions for RNG K epsilon turbulence model, I'm going to accept the default values for turbulence intensity and turbulent viscosity ratio. I am now going to apply another velocity inlet boundary condition at the second inlet. Again, I'm going to set up inlet velocity of 1 meter per second and an inlet temperature of 350 Kelvin. Also, I'm going to keep the default values for turbulence intensity and turbulent viscosity ratio for the RNG K epsilon boundary conditions. Or rather, sorry, for realizable K epsilon boundary conditions. So with that, I have one more boundary condition to go. I'm going to apply a zero static pressure boundary condition at the outlet because this outlet is essentially open to atmosphere. So I'm going to pick that particular outlet, and I'm going to accept all the default values, and that essentially sets up the pressure outlet boundary condition at that particular outlet. So the model specification is essentially complete. We have defined all the boundary conditions as well as initial conditions as well as the analysis settings. Now, before we go any further, you can right click on the screen and access Simulation Manager. So what Simulation Manager will do is it will give you quick access to all of the different things that you have created so far in your model. So you can see that you can access the flow regime, you can access initial conditions, you can access boundary conditions, you can also access the outputs that have been created by default. So you can edit all of those different things from here directly, or you can delete them from here as well. So now what I'm going to do is I'm going to modify one of the output boundary, one of the outputs that have been created automatically. So I'm going to request output only twice. So I'm going to request the output every 100 increments, because I have only 200 increments that I want the job to run for. So let's review the output variables that have been chosen. So you can see that pressure is chosen by default. What I'm going to do is I'm also going to include turb new and turb KE and turb EPS. So basically I am requesting K as well as epsilon as well as the turbulent viscosity for my flow simulation. The temperature and the velocities are already selected by default, so we don't have to really worry about those. So with this quick review of the output, I'm going to just close that and also start thinking of now submitting my simulation so that I can get the results. Before I run the simulation, one of the things that I want to do is I want to run my simulation on not on one core but at least on 4 cores, so that I get the simulation results faster. So one of the ways to do that is to go to preferences, simulation, and then execution, and then set up the total number of cores to the desired value. So in this case I'm going to select 4 cores. So that's it. My model is set up to run on 4 cores, and what I'm going to do is I'm going to go ahead and submit interactive run. So now you can see that the job has started running. The first thing is that the meshes are being generated, and once the mesh generation is complete, the job will be submitted. So the job has completed, and you can see that the results automatically show up, and you can see that the mesh also comes up by default. Now let's review the simulation status panel. So you can see that a variety of different quantities have been shown in the simulation status panel. For example, this is a steady state simulation, so the residuals for x, y, and z velocities, as well as residuals for turb KE and turb EPS, or K and epsilon, as well as the residuals for temperature show up, and you can quickly notice that those residuals have reduced at least 2 to 3 orders in magnitude. So the simulation is essentially converged, and we don't have to go back and check it again. Also, one of the things that you can notice there is that there is a plots panel which gives you access to all the increments. You can also right click on the screen to access the diagnostic viewer. In the diagnostic viewer, you have quick access to things like the data file as well as the status file, which gives you various quantities or various parameters of the simulation. So now the plots panel give you quick access to different plots that you are creating. So for example, you can see by default there is velocity, pressure, and velocity vectors plot. So those are available by default. It also gives you access to different increments. So now let's go ahead and plot the pressure. So you can see that I now have the pressure contours plotted, and on the right hand side you can also see the legends associated with the pressure contours. So you can actually open the option, the legend options, and you can toggle on show ISO contours in order to display the ISO contours for pressure as well. So as I toggle it on, you can see that the ISO contours are automatically plotted. Now one of the things that I want to do is I want to show the CAD or the pipe assembly as well along with my simulation results. So for that you have to go to the rendering settings, and in the rendering settings dialog box you have to toggle on show geometry, and once you toggle on show geometry you also have to activate material translucency so that you can actually see inside the so that you can see through the CAD geometry. So you can, as you can see now that I have activated the geometry as well as I have activated the translucency. One of the things that you note is that the mesh is also visible, so that's blocking our view, inside view of the results. So what I'm going to do is I'm going to bring up the specification tree by hitting F3, and I'm going to hide all the nodes and elements from the specification tree. So as I do that, you can see that the pressure ISO contours are visible now. Thing that you can do is you can also access these results from the simulation manager again, so that's quite convenient. One of the other things that I should have done before is that I should have hidden the glyphs for the abstraction or the fluid domain. So I'm going to do that through I'm going to hide it from the specification tree again. So you can see that all those glyphs that's for the inlet outlets and the fluid domain, they are now hidden. Now the next thing that I'm going to do is I'm going to plot velocity vectors, and again I'm going to keep my geometry visible so that I can see everything inside to give a reasonably good view of how the flow looks like inside my pipe assembly. Now the next thing that I'm going to do is I'm going to plot temperatures. So the temperature was not available in the plot panel, so I have to create a new plot. So for that I have to use the custom plot option and select temperature as a variable. So once I do that, the temperature is automatically plotted, and you can see that the temperature is now available in the plot panel. One of the other things that we can do during post-processing is using cut planes. So in this case, now I'm going to activate a plane which cuts the model right in the middle, and I'm just going to use a section cut so that I just see what is going on in the middle section of the pipe assembly. So as I see that, you can see that the mid section of the pipe assembly is now viewable, and you can see the temperature plot in that mid section. So once I do that, I'm going to deactivate the view cut, and I'm going to now create streamlines. So in order to do that, I'm going to use the stream toolset, and in the stream toolset, essentially what I'm going to do is I'm going to pick a bunch of points, starting points and ending points, and I'm going to select the total number of points that are going to be available or that are going to be used to generate streamlines on a particular stream. So in this case, I am selecting 10 points, and for advanced options, I'm going to use upstream, downstream and upstream for direction, and I'm going to use color from contours as the color for my streamline. So as I go ahead and hit apply, you can see that the streamlines are generated. So now I'm going to do create a bunch of more streamlines starting from the second inlet as well. So I created a bunch of more streamlines, and I'm going to select the other direction and create some more. Alright, so you can see that the contours, the temperature contours are also visible, so that's kind of hiding the clear view of the streamline. So I'm going to turn that off. So I access the simulation manager, and I'm going to open the temperature plot options, and I'm going to untoggle the show model. So once I do that, you can see that the contour plot for the temperature disappears, and now you have a better view of the streamlines which have been colored by the temperature. So with that, this completes the demo for setting up a thermal mixing simulation in a pipe assembly.